In this video, we will discuss how we can make use of the regression output from software. The software I use here is StatGraphics, but other software would provide very similar regression output as well. As we discussed the various procedures for interpreting the regression output, I will also ask 5 key questions. The first key question is a linear model appropriate to describe the relationship between x and y? The second question is, does x have any effect on y? The third one is, if yes, how large is this effect? And the fourth one is, given x, what is the estimated y? The last one is, how good is the current model? The dataset I'm analyzing here is the house size and house price example we discussed in the previous video. I randomly selected 24 houses from all the houses here in Corvallis and arranged them in 2 columns. It is important to notice that both variables are measured in thousands. Size is measured in thousands of square footage, whereas price is measured in thousands of dollars. When we try to use a simple linear regression to relate an independent variable with a dependent variable, the very first question we want to ask ourselves is whether a linear model is appropriate here. This is the first key question out of the 5 key questions. There are 2 methods to check whether a linear function is suitable to describe the kind of relationship between x and y. The first one is a scatter plot, and the second one is to perform a hypothesis test on correlation coefficient. For the first method, we can produce the scatter plot of house size and house price using StatGraphics. The commands are given at the bottom of this slide. From the scatter plot, it appears that there is a relatively strong and positive linear relationship between size and price. And yes, a linear model is probably appropriate to describe the relationship between size and price. The second method is to perform a test on correlation. Correlation coefficient is a measure of the strength of a linear relationship. The key word here is linear. The population correlation is usually denoted using Greek letter rho. Rho is typically not observable or unknown. The sample correlation is represented using small letter r. It is calculated from the sample. Correlation coefficient is always between -1 and 1. If correlation is +1, meaning 2 variables are highly positively linearly related. If the correlation is negative, meaning there's a negative linear relationship between x and y. Correlation only measures the linear relationship between 2 variables. For example, x and y here only have a correlation of a -0.12, which is very small. This does not mean x and y do not have any relationship with each other. It is clear x and y are related with some sinusoid relationship. A small correlation just means there's no linear relationship between them. Correlation coefficient measures the strength of linear relationship between x and y. We will carry out a hypothesis test to answer the first key question, whether a linear model is appropriate to model the relationship between x and y. We first use StatGraphics to produce a correlation table or correlation matrix. This can be produced using the commands given at the bottom. Sample correlation R is 0.9584, which is quite high. The largest correlation is 1. Sample size is 24. I selected 24 houses. P-value is 0. This is the p-value for the test given in the next slide. For this hypothesis test, the null would be there is no effect, meaning there is no correlation. So population correlation rho should be 0. The alternative would be there is correlation, so rho is non-zero. The alternative can be adjusted accordingly if we are testing to see whether there is a positive correlation or negative correlation. That is whether rho is greater than 0 or less than 0. We don't need to calculate the test this day like what we usually do. All we need is the p-value. P-value is close to 0. Therefore, we have enough evidence to reject the null, and we conclude there is a correlation between x and y, and a linear model is appropriate here. This concludes the first key question. Using the commands given at the bottom of this slide, we are able to produce a bunch of different output from StatGraphics all at once. There are two tables here, the coefficient table and ANOVA table. We will first focus on the first coefficient table that is highlighted in red. The coefficient table provides both the intercept and slope coefficient estimates. Therefore, we are able to write down the estimated regression model or least squares model. That is, y hat is negative 15.1245 plus 76.1745 times x. Writing down the model is not everything. We would like to be able to interpret this model as well, especially the slope coefficient, that is beta 1 hat. It can be interpreted this way. For every 1 unit increase in x, estimated y increases by 76.1745 units. This can be translated to, for every 1,000 square footage increase in size, price goes up by $76,000. The keyword here is every. Because the relationship between x and y is completely linear, the change in y or effect of x on y is always the same regardless whether we increase x from 1 to 2 or from 1.75 to 2.75. Based on the coefficient table, we can also answer the second key question, that is whether x has any effect on y. The effect of x on y is measured using the slope coefficient. The null would be x has no effect on y, meaning for any change in x, y does not change at all. So the slope coefficient, or beta 1, should be 0. If x has an effect on y, beta 1 should be non-zero. The alternative is beta 1 is different from 0. The test statistic would be a t-statistic. It has the Euro form of estimate minus the null value divided by the standard error. The null value would just be 0 because we are comparing beta 1 with 0 in the null and alternative statements. The standard error is actually presented in the coefficient table, and the t-statistic can be calculated using the formula to be 15.7435, which is also given in the coefficient table. To carry out this hypothesis test, we would also need to find the degrees of freedom for this t-test. The degrees of freedom would be sample size n minus k minus 1. K here represents the number of independent variables in the model. We only have one x in the model, so k is 1. The degree of freedom is 22. Using the t-table, we should be able to find the upper-tailed probability for 15.74 is almost 0. The p-value for this two-tailed test would be twice of that probability, also very close to 0. We reject the null and conclude the beta is non-zero, and yes, x has a significant effect on y. For some other data sets, we may fail to reject the null and conclude x does not have a significant effect on y. What we usually do is to remove x from the model, because x is not a significant factor in explaining y. This concludes key question number 2. If our answer to key question number 2 is yes, that is, x has an effect on y, subsequently we may be interested in estimating this effect or ask ourselves how large is this effect. This is a key question number 3. This question is an estimation problem, no longer a hypothesis testing question. We can estimate this effect by developing a confidence interval, say at 95% confidence level. This is fairly similar to what we have learned before. A point estimate plus minus MOE. Point estimate is just a slope coefficient estimate, that is beta 1 hat, that is 76.1745. The MOE is the product of a t-multiplier and the standard error of the slope coefficient. The standard error is given in the table, that is 4.83848. The t-multiplier can be found using the t-table. It's 2.074. The effect of x on y is estimated to be between 66.14 and 86.21 at a 95% confidence level. This can be again converted to $66,000 and $86,000 for each 1,000 square footage increase in the size of the house. Key question number 4 is about how to make use of the estimated model to do predictions. For example, We may become interested in estimating the house price for a 2,000 square footage house. How would you do that? You may remember that previously we derived an estimated linear regression model, which is given on the right. We know the size of the house is 2,000 square footage, so x is 2, not 2,000. Plugging 2 into the estimated model, we are able to calculate the estimated house price. So now you probably see how useful linear regression models are. They do allow us to do predictions for almost any values of x. There are certainly situations this won't work very well. For example, when the new x is outside the range of x, we may not be able to do predictions for houses that are much bigger or much smaller than those 24 houses I selected. This is because the linear model may not be valid for those new x values. Predictions using estimated model are easy to perform. There are two different types of predictions. Let's consider the following two cases. Case 1. There is an orange house on the 9th and Monroe Street. I really like this house, and ask my real estate agent about it, and learn the size of this particular house is 2,000 square footage. What's the estimated price of this house? Case number 2. I like to purchase a house with 2,000 square footage. My real estate agent found a total of 50 houses in Corvallis with exactly 2,000 square footage. What's the average price of these 50 houses? These two situations are somewhat similar to each other. We want to estimate a house price for one particular house in case number 1, and we want to estimate the average price of 50 houses in case number 2. The houses we are looking at here are all 2,000 square footage, so x is always 2 in both cases. It's actually not surprising that the point estimates for both cases are the same. The difference lies in the uncertainty associated with these 2 point estimates. You may want to think carefully whether we are more certain with our estimate in case number 1 or case number 2. In the first case, we estimate a house price for one particular house. Our estimate could be higher or lower than the actual house price. In the second case, we estimate the average price of a bunch of houses. You may remember from the CLT module that averaging reduces variability. When we estimate the average price, our estimate will become more certain than the estimate for one particular house. Therefore, the second interval is narrower because we are more certain with the estimate, and the first interval is wider. The first interval is also known as the prediction interval, and the second interval is the confidence interval, which we are quite familiar with. These two intervals can be produced using star graphics. As we can see here, both intervals have the same center, but the prediction interval is wider than the confidence interval. This plot can be produced using the commands given on the next slide. These are the detailed commands to do prediction and produce prediction and confidence intervals using star graphics. After we did all this work to estimate this model and to do predictions using this model, it is very important to say whether this model is a useful one or not. If this model can be evaluated to be good, we should feel comfortable to use the size of the house to predict the house price. On the other hand, if this model is not useful or not good, we should not use it to estimate price based on the size. We will discuss 4 different approaches to evaluate linear regression models. To be considered as a good statistical model, it's essential that this model passes the criterions using all 4 methods. The model is not a good one if it satisfies the criterions using the first 3 methods but fails the residual analysis. The first method is ANOVA. You may remember the second table in the regression output is the ANOVA table. This ANOVA table is similar but not identical to the ANOVA table for multiple mean comparison. Let's start off by setting up the ANOVA table for linear regression first. This is again an analysis of variance, so we would like to partition the total variability into 2 sources. The total variability, or SST, here refers to the total variability of variation in the dependent variable y. It can be divided into 2 sources. the part of variability that can be explained by our regression model, and the part that cannot be explained by the regression model. The part that can be explained is denoted as SSR, where R comes from regression model. The unexplained variability is left in the residuals. You may remember from previous video that we use E to represent residuals, so this is also called SSE. Therefore, SST is the sum of SSR and SSE. You could also add up SSR and SSE in the table on the right to see whether their sum is the SST given in the table. It's important to know that if two of these three sums of squares are given, you should be able to calculate the remaining one using this equality relationship. The degrees of freedom for the model is k, which is the number of independent variables in the model. This number is always 1 for simple linear regression, because there's only one independent variable. The degrees of freedom for the total is the sample size minus 1. The degrees of freedom for the residual is the difference between the degrees of freedom for model and the total degrees of freedom. You may also double-check this formula against the table on the right. I selected 24 houses. The total degrees of freedom is 24 minus 1, that is 23, as seen in the table. Mean square is the sum of squares divided by degrees of freedom. The test statistic is an F ratio, that is the ratio between MSR and MSE. Now you may become curious what exactly this F-test does. Previously, the F-test for multiple mean comparison is to see whether all population means are the same. We don't have multiple populations here. How can this F-test be relevant for linear regression setting? The null for this F-test is actually the current model is useless. More specifically, this model with both intercept and slope coefficients is not any better than a model with only intercept. The alternative for this F-test is the current model is useful, meaning it's superior than a model with only intercept. The test statistic is calculated to be 247.86. This can be also seen in the table on the right. The degrees of freedom are 1 and 22 respectively. We can look up the p-value for this test using F-table, or we can use computer software to calculate it. StatGraphics tells us the p-value is 0. We reject the null and conclude this model is useful. We will now move on to the second model evaluation method using R-squared. R-squared is defined to be the percentage of variation that can be explained by the regression model. It's a number between 0 and 1. We would prefer models with high values of R-squared because it implies these models are able to capture and explain a large percentage of variation in the dependent variable. A model is considered to be good if R-squared is at least 70%, but this number of 70% can vary across different fields. From the regression output, we can see that R-squared for our model is almost 92%. Way larger than 70%. Thus, our model is useful. Sometimes the R-squared may be missing from the regression output. That means we would have to calculate it on our own. There are two different methods to compute R-squared. The first one is to use the definition of R-squared. It represents the percentage of explained variation. So we just have to use the amount of explained variation, that is SSR, divided by the total variation, SST, so SSR over SST. Using the SSR and SST given in the table on the right, we can verify their ratio is indeed R-squared. The second method to calculate R-squared actually originates from the name of this coefficient. It's the square of R, where R is the sample correlation. Sample correlation coefficient is given to be 0.958371 in the table on the right, so R-squared is just the square of correlation coefficient. These two methods work equally well for simple linear regression, but the second method fails for multiple linear regression. Now we move on to the third model evaluation technique. This technique is based on the size of a standard error of estimate. Standard error of estimate measures the spread of data points around the fitted line. The model is considered to be good if all points are quite close to the fitted line, meaning the spread is small, so standard error of estimate is also small. Standard error of estimate can be calculated using the square root of MSE. Taking the square root of 173.785, we are able to verify the standard error of estimate is indeed 13.1448 as shown in the table. The drawback of using standard error of estimate to evaluate a model is that it's difficult to tell whether our standard error of estimate of 13.1448 is small enough. This method is more useful when we compare several models for the same dependent variable, and we would prefer the model with the smaller standard error of estimate. The very last model evaluation tool is residual analysis. In this method, we would check to see whether any of the model assumptions is violated using residual clause. We have imposed several important assumptions on the model. These are the assumptions on the structure of random error. You may remember this scatter plot from previous video. Random errors are not observable. We would have to use of the patterns of residuals to check whether the assumptions on random errors are appropriate or not. These are the 4 assumptions for linear regression models. They can be summarized using 4 letters, L-I-N-E, line. L stands for linearity. The relationship between x and y is assumed to be linear. I stands for independence, independence of errors. The errors are independent of one another. N stands for normality of errors. The error around the line of regression is normally distributed at each value of x. E stands for equivariance, also known as homoscedasticity. The variation around the line of regression must be constant for all values of x. We have already checked the first assumption in key question 1, that's regarding whether the relationship between x and y is linear or not. The remaining 3 assumptions will be checked later on using the residual clause. Residuals can be calculated using actual y minus estimated y from our estimated linear regression model. We examine the residuals or some other versions of residuals to detect any violations of the assumptions on random errors. In this table, I will demonstrate several different versions of the residuals. For the first house out of 24, its residual can be calculated using actual y minus estimated y. So 150 minus 144.84, that's exactly 5.16, as shown in the residual column. The standardized residuals in the next column are just the z-scores of the residuals. The studentized residuals are fairly close to the standardized residuals. We will not go over the detailed formula to calculate the studentized residuals here. All we need to know is it's quite close to the standardized residuals, which are z-scores for the residuals. Let's take a look at the independence of errors assumption. So in this assumption, we assume the errors are independent of each other. So first, we would have to produce a residual clause. The residual clause can be produced using star graphics, and the comments are given at the bottom. So what to expect if this assumption is satisfied? If errors are indeed independent of each other, the residuals should look like randomly distributed, and we do not observe any clear pattern in the residual clause. From our studentized residual clause, it looks like the residuals are randomly distributed, and we do not observe any clear pattern. So it looks like the independence assumption is valid. These are some examples when the independence assumption is not valid. For example, in the first one, the residuals are not independent from each other because there are runs of positive residuals followed by runs of negative residuals. On the second plot, we can also see there are some kind of oscillating behavior of the residuals around 0. So in both scenarios, the independence assumption is not valid. The next assumption is normality of errors. We assume the random error being normally distributed. What to expect if this assumption is satisfied? We're going to use empirical rule to check this assumption. Empirical rule says about 68% of the residuals should fall anywhere between plus minus 1, 95% between plus minus 2, and we do not expect to see any residuals fall outside the plus minus 3 range. By looking at our residual plot, it looks like this normality assumption is also valid here. The last assumption is equal variance, also known as a homoscedasticity. We assume the error variance to be constant for all values of x and estimated y. What to expect if this assumption is satisfied? Residuals should scatter around zero line with constant spread, so variance should stay about the same across the entire residual plots, regardless whether the horizontal axis being x or estimated y. When the constant variance is not satisfied, we have a condition that's known as a heteroscedasticity. To be able to detect whether we have constant variance, all we need to do is plot the residuals against the predicted y, against the actual y, and also against each independent variable x. It looks like the residual spread increases with estimated y, so we do not have a homoscedasticity. The constant variance is not satisfied in this toy example. But for our house example, it looks like the constant variance is satisfied. So in conclusion, all 4 model assumptions are valid for our house example. What to do if there is a serious model violation? First, we can examine to see whether the assumption of linearity is valid. And also we can take a look to see whether there are any insignificant x in the model. That means those x does not have any important effect on y. And then we're going to remove them one at a time. We can also take a look to see whether there are any important x's that are not included in the model and are not accounted for. We can add them to the model. We could also examine the outliers to see whether there is any reason to remove them. Lastly, we can talk to a field expert. This concludes the simple linear regression model. To work on simple linear regression models, we asked ourselves the following 5 key questions. Again, the first question is a linear model appropriate? The second one is, does x have any effect on y? If yes, how large is the effect? And given any x, can we predict the estimated y? And lastly, how good is the current model?